So in this lecture slideshow, we're going to go over chapter 4, which is the last of the 4 chapters that will be included on the Module 1 exam. And this is probably the most critical chapter out of the first 4 chapters because of the calculations for variability. So you'll want to pay close attention to the steps when we go through, and then also utilize the videos that I have on calculating measures of variability. So let's go ahead and get started. We'll talk about what variability is. So variability basically tells us how spread out or close together data is in a distribution. So basically, if we have a distribution of scores, it tells us whether they're clustered close together or whether they are spread out far apart, is what variability is. Now, variability is this umbrella term, just like measures of central tendency. Measures of variability is an umbrella term that incorporates other aspects or measures specifically. So with variability, we can have any number from 0 to infinity, but it can't be a negative number. So it doesn't make any sense for variability to be a negative number. So either they vary or they don't vary. So if all the scores are the same, every score is the same, your variability is 0. If you have a -3 variability, it doesn't make sense. So either there is variance or there is not. So it tells us how much the scores differ from one another. So variability is, again, this umbrella term, an overall general term. So there are 3 measures of variability, just like there were 3 measures of central tendency, which was the mean, median, and mode. Now we have 3 measures of variability. We have the range, variance, and standard deviation. And so we're going to talk about the differences between these 3 measures of variability, how you calculate them, and what they're used for specifically, and how we will be using them. So let's go with the most basic. And I'm sure that you have all done the range before or calculated the range before. It's really just the difference between the largest value in a set of scores and the smallest value in a set of scores. So as you could see, I have L minus S or H minus low because people figure these differently. Like L minus S could be if you're looking at largest number minus smallest, or I always do highest number minus lowest number. It is just a really kind of simple way of describing how scores range. So let's say we have our exam 1 scores. You can score anywhere from 0 to 100. But let's say I'm trying to explain how scores fell. I say, you know what, the majority of the students did really well. Our range was a range of 30. That means if basically if you did well, that means the scores only varied between 30 points, probably on the high end. In actuality, the potential could have been 100 points, but everyone fell just within 30 points. So that was a really narrow, clustered range of scores. So as you can see, if we have scores 1, 2, 3, 4, 5, it's just 5 minus 1, which is 4. And then, even if we have 2, 4, 6, 8, and then this high number of 100, the range is 98 because the highest number is 100 and the lowest number is 2. So this is a little bit different than what you did with the grouped frequency distribution where you got the real range. That was to include the upper and lower limits. When you're measuring variability, you just get the range, a straight range, highest minus lowest, no adding 1 to it. So it's just very simplistic, rudimentary way of describing how the scores are dispersed. It's useful in some cases, but not usually the main measure of variability that is discussed in research. We will discuss variance and standard deviation. So variance is the next measure of variability you're going to learn. And if we look at this definitionally, it's very important to know the variance measures the average squared distance that the scores deviate from the mean. So let's say if the average distance the scores are from the mean is 2 points. So on average, scores vary by 2 points around the mean. The variance is actually 2 squared. So variance is the squared distance. So one way of kind of remembering that it's the squared distance is that even if you look at these notations, you'll notice the squared symbol next to their notations, the squared. So these are the notations for the different types of variances. There's a different notation for population than there is for sample. So it's really very, very, very important for you to notice that this is the population, this lowercase omega squared. And the sample notation is a lowercase s squared. Now, it is important for you to use the right notations because the calculations are different. And basically, when we're reporting information, we are reporting using notation so that we don't have to write out this whole sentence, variance for a population is, and then write the number. If we just use the right notation, that notation in itself tells us whether we're dealing with a population or a sample. So that's just the notations that you're going to need to learn. And every parameter or statistic that you report must have a notation if there is one available. So it should always be the notation followed by the equal sign, not a colon, an equal sign, followed by the value that is calculated rounded to 2 decimals. So it's always in that format for APA research. So you need to make sure you're in the right format. So your textbook gives you a couple of different methods for calculating variance. I only want you to learn one way. It is the most common way, and the reason why it's common is because it's accurate. The definitional method that the textbook uses is prone to rounding errors, rounding problems, and is only really, really beneficial if you're using very, very, very simplistic data, whole numbers, small numbers, whereas if you're dealing with real research data, you're going to want the most accurate method. So I only teach the computational formula to calculate variance. Now, it's very, very, very important that you pay close attention to what is going on in these formulas. So if you'll notice, the population notation for variance is followed by the equation, which is SS over capital N. If you remember, capital N is the size of the population, the number of participants in the population. So that's why it's a capital N. Now, SS is a notation. So if you'll notice, here's SS, and it is specifically a notation. It is not a calculation. It's a notation. So SS is a notation within that equation. So is what you're actually calculating with SS is this right here. It's the sum of x squared minus the sum of x total squared divided by n. So, and this entire equation goes right here. So this n does not represent this in. This is no. It does not. So no. I'm going to write no there. That's not that n. It's a whole different n. So is what you would do is calculate the sum of x squared, and then you would subtract this fraction from it, and then that total you would get, you would put into this SS location. So that's for a population. Now our sample is a little different because samples have more variability. So we'll talk about what that means. But the sample, which the notation is s squared, is the same. It's the sums of squares, but now it's divided by n minus 1. And n minus 1, there's also a notation of d of f. So that's the same thing, and we'll talk about what that means, okay? Again, in this case, sums of squares, this SS, is calculated the exact same way as it is for population. So this entire equation really goes right here, is where it goes. And then when you calculate that, it's divided by n minus 1, or what's called the degrees of freedom. And we'll talk about what degrees of freedom are. So degrees of freedom, because samples are never a perfect representation of the population, there's always going to be a difference, some error between the sample and the population. No matter how great of a sample you have, it's going to differ a little bit from the population. So the sample is usually an estimate. So is what we have to do is estimate what we would see in the population, and we have to take into account that the sample variance is going to be different or less than what the population is going to be. So is what we have to do is take into account the bias, which we do with what's called degrees of freedom. So definitionally, degrees of freedom is the number of scores in a sample that are independent and free to vary. So every single score in a sample could be any number. There's only one score that is not going to vary, and that's the mean. So that's really what you're doing, is you're taking account the mean, and this was a way that they found, oh, this can account for the fact that samples have a bit of a bias because they're not exactly a duplicate or a replication of the population. So when we're dealing with sample variance, we have to use degrees of freedom in that denominator. So that means the sample variance is calculated differently. That's one of the reasons why they have different notations, is so that you can tell whether it's a sample or a population. So we'll go through the steps for calculating sums of squares, because that's where the computational formula comes in. So I have a list here of raw scores. So here where you see X is these raw scores, 14, 23, 28, et cetera, et cetera, et cetera. So I have this here so it can show you how we would calculate things. So this sum of X, if you'll notice, if you add all these up, it's 996. So if you'll notice right here is sum of X. These parentheses means you need to add up the X scores and put that number there. You don't square it yet, you wait until after. So that's why I put the 996 here, right here. And this is probably one of the biggest mistakes students make, is mixing up this sum of X squared and the sum of X total squared. They mix those two up. Now this, if you'll notice, this is X squared versus X. That means every raw score should be squared and then added. Now, I have this here as an example, like 14 squared is 196, 23 squared is 529, 28 squared is 784. I have this as an example, but I do not recommend you writing down every raw score squared and then plugging into your calculator. The reason is that leaves a lot of room for data entry error. If you'll notice this, I have kind of the screen of this calculator, and hopefully you have a calculator that has a running screen. If not, you might have to chunk your information. But if you notice, there's 14 squared plus 23 squared. So what I've done is I'm putting these in right, just the raw scores, and then putting the squared symbol. So this keeps you from having the data entry error. Then if you have this running list of squared numbers before you hit enter, you can double check that you haven't made an error before you hit enter. So note that on many of your calculators, there is a squared button. So mine is right here. So if I was to do like 2 squared, I would just go 2 squared. You don't have to do the caret. And any scientific calculator should have that function. So just learn your calculator and utilize those resources. So once you square every one of the scores and add it up, you get this total, and that is the number that gets plugged in right here. So sum of x squared comes here. So these are all the squared scores, where this is just the raw scores added and then squared. And then this n is 20. And if you just count how many scores there are 20 scores. So we end up with a sums of squares of 11,199.20. Okay, we're not done yet. That's not the variance yet. That is the sums of squares. So we can actually start using that information to plug in. So if we were computing a population variance, we would plug in that 11,199.20, and we would divide it by 20 because that's n. And our population variance would be 559.96. But if we were doing for a sample, okay, we would plug in the n minus 1. So we would minus 1 from 20 and plug in 19. 11,199.2 by 19, and the sample variance is 589.43. If you notice, this is higher because what we've done is accounted for the fact that samples often have less variance than the population. So what we do is we overcompensate so that we can account for that variance issue that we're seeing with the samples. So we account for the potential of having less variance overall. And so it is higher, but that's because we're taking into account the fact that it is a biased sample. So once we have calculated our variance, this is the nice part. So we've learned the measures of variability of range and variance. The next one is standard deviation. Standard deviation, it literally has basically the same definition as variance, but this is the average distance that scores deviate from the mean. So I used the example of, if on average scores deviate from the mean by 2 points, that is the standard deviation, whereas the variance, it would be 2 squared, which would be 4. So variance is the squared distance. Standard deviation is the average distance. And so this is actually what we see reported the most because it makes much more sense than the squared distance. But we have to get variance to get standard deviation. So again, we have 2 different notations. If you notice, it's the same notation for population, but without the squared, because now it's not the squared distance. So we have the lowercase sigma, and then we have for standard deviation, you could use lowercase s, or I frequently use capital S, capital D for standard deviation because that is the APA accepted. But your textbook uses both. It has introduced both because they're both acceptable notations for the sample. So when we calculate the standard deviation, it's as simple as calculate your variance, and then take the square root of that variance. So here, if you'll notice, the standard deviation is the same equation as the variance, but with a square root over the top of it, right? So standard deviation is the same as the sample variance, but with the square root over it. So in actuality, you can just take your variance that you calculated and take the square root of it. So whatever that answer is, you take the square root of that to get your standard deviation. Again, it's important to know your notations, because if you're reporting a sample standard deviation, it should be either lowercase s or capital S, capital D, to specify that is it sample standard deviation. So here's what we would be looking at. Bear with me a second. Okay, here's what we would be looking at for the calculations that we did. So we have the 559.96, which was the population variance. We just take that square root, and we end up with 23.66. So this is what we would show as the standard deviation notation equals 23.66. The sample, SD equals 24.28. So it just took that sample variance and took the square root of that variance to get the standard deviation. So once you get the variance, it's fairly simple after that. So why we find standard deviation is such an important measure of variability, because for the remainder of the semester, we're going to be talking about distributions, and we're going to be using normal distributions to compare everything to. So if we have a sample of scores, we're going to compare it to a normal distribution to see, does it fit? Is it significantly different? Is it very similar? Does it fall within the same averages of the population? These types of things. So there's rules. If we have a normal distribution, we know very specifically that 68% of the data is going to fall between one standard deviation above the mean and one standard deviation below the mean. So it doesn't matter what the mean is or what the scores are. If it's a normal distribution, meaning a perfectly bell-shaped curve with 50% on one side and 50% of the data on the other side, 68% of the data is going to fall between one standard deviation above and below. And then again, 95% of the data is going to fall between two standard deviations of the mean, two above and two below, and et cetera, et cetera. And 99.7% of the scores will lie between three standard deviations of the mean. So 3 standard deviations above, 3 standard deviations below. We can assure this as long as we're using a normal distribution. And so that's what we're going to be comparing everything to when we're conducting research. So it's important to understand how a standard deviation works within that normal distribution, and why it's important for us to know kind of where things fall. So we'll be using more of that in the next chapters, much more with standard deviations and the normal distributions. So there are some important things about standard deviations. You'll want to kind of focus on these when you're doing your calculations, because if your calculation comes out and it contradicts any of these characteristics, you probably have an issue with your calculations. So first of all, standard deviation is always going to be positive. So it's going to be either 0 or anything above 0. It cannot be a negative number. And if you remember, standard deviation is basically the square root of variance. And remember, variance is the average squared average squared distance. The scores vary from the mean. So if you're squaring numbers, they're going to be positive. Any number squared is positive. So if you get a negative number with your standard deviation, you know you've done something wrong. So these are important rules to kind of remember. Standard deviation is only able to describe quantitative variables, so variables with values. So the number values are meaningful. The number 2 really means it's one more than the number 1. It's not just a placeholder. Like when we enter data into PSPP or SPSS, I'm sorry, which are our statistical software programs. If we have a variable like gender, these programs don't use the names. They actually assign numbers, but the numbers are meaningless. So like a 1 would be a male, a 2 would be a female, but a female isn't 1 less than a male. So those are meaningless numbers. They're not quantitative. So you can only use standard deviation to describe quantitative variables. Other important things is the standard deviation is typically reported with the mean. So it's kind of useless information if you just report just a standard deviation. It's usually reported with the mean plus or minus standard deviation. So if we had a mean of, let's say, 50, okay, I would put 50 here, and then our standard deviation for that sample maybe is 5. I would do plus, minus 5. And I know this is very sloppy, but that is how it would be reported. It's automatically assumed the mean comes first, then the plus or minus is standard deviation. Plus or minus meaning the scores on average deviated from the mean above and below the mean by 5 points. So you know that one standard deviation above 50, the mean of 50, the score you would find would be 55, because 50 plus 5 is 55, if that makes any sense, and it will down the road. So, and then the standard deviation is affected by any score in the distribution by every score. So it's similar to measures of central tendency with the mean. So if you add a constant to every score in the mean, the mean would shift by that amount. If you added let's say if the mean of our exam 1, let's say the average score was a 75%. But maybe I found like one of the questions on the exam was not worded very well, and the majority of students missed it, and that was worth 2%, the one question. So I decided to add 2% to everyone's scores. Well, the mean would shift from 70% to 72%, but the standard deviation would be the same, because the variance doesn't change. It's just you've shifted the whole distribution over by 2 points. They're still the same variance. And so this is important to understand. It doesn't actually change the variance. If you change one score, yes, it will. But if you're changing them all by the same amount, then it will maintain that same standard deviation. So it's just you're shifting the scores over just a little bit. So these are just some things to think about when you're kind of picturing the mean and standard deviation as part of that distribution of numbers. So the whole purpose of variability is to kind of help us to determine patterns in research data. So the whole point of inferential statistics, right now we're dealing with descriptive statistics. The whole point of inferential statistics is to find patterns and to be able to use research results to infer about the populations? Well, if we take measures of variability, we're able to see these patterns. And if we have a low measure of variability, then we're going to see patterns very easily. So if we have a high variability within our data, it means that it's going to be more difficult for us to see the patterns in the data. So that's why variability is often called error variance, because if the variability is high, there's going to be a lot more error in the patterns that we're seeing. So this is going to be used for the entire semester. So if there's anything that you really get down, is the measures of variability, what they do, what they mean, and calculating them. Because everything we do from this point on is going to be using measures of variability, especially variance and standard deviation. So practice this, learn it, ask questions about it, and kind of perfect it, and make sure you get all the notations down. So I just threw in kind of an example. So when you're conducting your lab or bringing your lab together, you're going to notice, you know, I asked you to report things like the measures of variability. I am not looking for you to just copy and paste this box that you get from PSPP or SPSS, sorry. I am looking for you to communicate it to me as if I do not know how to read these tables. So here I have an example. Here's a sentence. The measures of variability for daily spending. And how do I know this is daily spending? It shows right here. So this is our variable, must be our dependent variable. So the measures of variability for daily spending showed the range equals 900, and I would, because 900 is, it doesn't have any decimals, I would accept a whole number for 900 or 900.00. So, and range does not have a notation, so I use the whole word equals and then the number. Variance, S squared, because this is a sample, you know, it says here sample, is 37,340.79. If you'll notice right here, this says 37,340.786. Well, that's 3 decimals. When you report, it should be to the second decimal. So 0.79, because 6 is higher, is 5 or higher, so that 8 goes to 9. And then last, and standard deviation equals 193.24. Again, this was rounded to 2 decimals, so that you're complying with the APA. So when I ask you in your lab report, you know, provide me the 3 measures of variability, I'm looking for something like this sentence right here, and with notation. So be really cognizant of your rounding as well as the proper notations, because these right here, the S squared and the SD, are telling me that this daily spending is a sample. You don't have to even say sample in here, because if you're using the right notations, that says it right there. It's a way of simplifying the information. So hopefully that helps you to get kind of a general understanding of the measures of variability. Please go on and watch the videos on measures of variability. It will help you, and use and practice those active engagement practice activities, because this is not stuff that you can just learn by listening, and you're going to have to practice over and over and over again. And don't hesitate to ask me any questions. Come see me during office hours, or set up an appointment outside of office hours so that I can help you if you need. And I can also help you with your calculator usually. So if you have that with you, we can talk about it, and you can show me virtually what your calculator looks like, and we can figure out how to use that. So hopefully this all wraps everything up for you, and you can complete your homework. Good luck on exam 1.